Evaluate the expressions for the given value of x. We have the expression negative 3x cubed, and we're asked to substitute a 2 in for x. We place a 2 in here in parentheses. Be sure to apply exponent before you multiply. If you multiply three 2's together, 2 times 2 times 2, that gives you 8. 8 times negative 3 is negative 24. In the example at the upper right, we have the expression 7x to the negative 2 power, and we're asked to substitute in a 9. If you see a negative exponent, you can take that term across a fraction bar and the negative goes away. This expression is equivalent to 7 over x to the positive 2. When we sub in a 9 for x, two 9's multiplied together give us 81, so this expression has a value of 7 over 81. Reviewing a few exponent properties, 7x quantity cubed. Remember that exponents are just shorthand notation for repeated multiplication. So this is actually 3 7x's multiplied together. When you multiply algebraic expressions, you multiply the coefficients. 3 7's multiplied give you 343. And then you also keep a running total of the exponents of your variable as you go. Now, since these are all x to the first, and there's 3 of them, there's x cubed at the end. Our expression in the middle is 8x to the 4th over 2x to the 7th. 8 divided by 2 is 4. Now, where we get this x cubed left over on bottom is x to the 4th. That's x times x times x times x. It's 4 x's multiplied together. On the bottom, you actually have 7 x's all strung out and multiplied together. If you cancel 4 of those x's from the top and 4 x's from the bottom, it leaves 3 of them remaining in the bottom of the fraction. The example to the far right, 6 times y to the negative 3 multiplied by 3y to the negative 5th. When you're multiplying, you multiply coefficients. 6 times 3 is 18. And for variables that are the same, you add the powers. Negative 3 plus negative 5 is negative 8. If WebAssign asks you to rewrite with positive exponents, all that means is take your term with a negative exponent, carry it across the fraction bar, and that exponent becomes positive. Rewrite each number in scientific notation. In the beginning, we have a large number, 42,091 and 3/10. In scientific notation, you want your first number to be between 1 and 10. So in order to make that happen, I need to put a decimal right behind this 4. In order to do that, I have to move this decimal point 4 places. To get the decimal point after it's put behind the 4 back to its original location, I have to move it right 4 spots. In the second example, in order to create a lead number that's between 1 and 10, I have to move a decimal behind this 2. So that's negative 2.82. To get that back to its original location, I have to move it left 4 spots. So that's why my power of 10 is a negative 4. To get the decimal back to its original location, in large numbers, you have to move it right. In small numbers, you have to move it left. Evaluating square roots, square root of 25 is 5. Why is that? It's because you have to have 2 5's multiplied to get 25. Since 5 squared is 25, the square root of 25 is 5. The upper right example, we have a cube root, so we need to figure out what it takes 3 of to make 343 over 27. You can cube root these separately. The cube root of 343 is 7. 7 cubed is 343. The cube root of 27 is 3 because 3 3's multiply out to 27. So just remember, with a cube root, it's your answer, and it takes 3 of those to multiply back out to the original value, whereas a square root, you only need to have 2 of them to multiply back out to the original value. Some properties of radicals: if your root and your exponent match, cube root of 4 cubed, they'll directly cancel one another and you just get the radicand. In this case, it's 4. The cube root cubed, they undo each other, so you have 4. Underneath the radical on a cube root, this upper right example, now because that's 27 times x cubed, you can split this up into 2 separate cube roots, just as long as you keep them multiplied. The cube root of 27 is 3 because it takes 3 3's to multiply out to 27. When it comes to variables, the exponent gets divided by the root you're taking. So 3 divided by 3 is 1, leaving us with 3x as the answer. Now, if you think about it, if you multiplied three x's together, you would get 27x cubed. The bottom left example, well, I'm going to move it up. So now the top left example, square root of 24x cubed. 24 is not a perfect square, but it can be written as 4 times 6 because 4 is a perfect square. We can reduce that to 2. This 6 we can't do anything with, so it's going to stay underneath a radical. X cubed, 3 is not evenly divisible by 2, but we can break this up into x squared times x to the first. That way we maintain all 3 x's, but we write them such that we can divide some of it by 2, even though we can't divide all of it by 2. This absolute value, it's a little quirky thing that shows up when you ever reduce a variable through a root. If the original exponent is even, but after dividing becomes odd, you put absolute values around it. Remember, you're not supposed to really have a negative under a square root, and so that addresses that problem. But anyway, long story short, 24 is 4 times 6. Square root the 4, leave the 6 behind. Rewrite x cubed as x squared times x to the first. X to the 2 divided by 2 becomes x to the first, but because we went from even to odd, put absolute value around it, and then this little single x just stays underneath. Square root of 80, 81's a perfect square, but 80 is not. Although we can write 80 as 16 times 5, 16 is a perfect square, and its square root is 4. This 5 we cannot square root exactly, so square root of 80 reduces to 4 square root of 5. Rationalizing the denominator, if you have an expression where a radical or a square root is in the denominator and you're asked to perform this operation by rationalizing, all you're doing is creating the same numerical value, but it no longer has a square root in the denominator. How do we do it? We force the denominator to become a perfect square. Take your original problem, multiply both sides of that fraction by your radical term. In this example, it's square root of 6. 1 times square root of 6 is square root of 6. Square root of 6 times square root of 6 is square root of 36, which is exactly 6. And so this number is the rationalized form of that number. They have the same value, it's just this one no longer has a square root in the denominator.